Alright, so in this video we're going to show that the force between a shell and a mass when the mass is inside the shell is going to be 0. Okay, so let's do a calculation of this. This is going to be a lengthy calculation as well, but it's something that, you know, once again, it's some you should learn how to do this. So once again, what we have is we have a shell. We will take a ring, and now in this case the mass is somewhere here. Okay, so this mass m is here, and we have again the distance from the center is x. The radius of the shell is r, the angles are thetas and phis, and we have the r sine theta in the picture. Then the length here, this length is r cosine of theta, and once again this distance here, okay, is equal to x minus r cosine of theta. So this gives us the distance of any point on the ring from the shell to be the same as the last one, where it will be equal to r square plus x square minus 2xr cosine of theta. And once again, from symmetry we know only that the horizontal component survives due to the ring, so once again we need the cosine of phi, which ends up being equal to x minus r cosine of theta divided by square root of r square plus x square minus 2xr cosine of theta. Okay, so we have this. Now having said all this, our df ring is going to have pretty much the same expression as what we had earlier, okay, which would be capital G M M over 2 times, and what we're going to do now is, once again, we're going to integrate from 0 to theta, sorry, 0 to pi for all the elements of the ring. Okay, and okay, so I've just rewritten the expression here, okay, which is identical to what we had in the beginning, except that there's one big change here. If you look at this x is going to be less than r. Okay, so when we make our substitution, when we do the u substitution for the denominator, what we have to keep in mind is that the limits there are going to be from r minus x to r plus x instead of x plus r, or x minus r to x plus r as in the previous case. Okay, and that little thing can make all the difference here. So let's go ahead and write down our substitution. We're going to do this. Okay, so this again, differentiating both sides, we end up getting negative 2xr times negative sine theta equals du, and this ends up giving us du is equal to, sorry, there's a d theta here, this ends up giving us sine theta times d theta is equal to du divided by 2x times r. Okay, and now once again, as I said earlier, our limits when theta is equal to 0, u will be equal to r minus x, and when theta r minus x the whole square, and when theta is equal to pi, u is equal to r plus x the whole square. And also what we know is that cosine of theta is equal to r square plus x square minus u divided by 2x times r. Great. So we have all our components, and now we can plug it into the force for the ring. Okay, we shouldn't be writing F ring anymore. It should be D. It should be the total force. So total force will be G M M over 2 times integral of r minus x the whole square to r plus x the whole square. The sine theta d theta term ends up being equal to 2 du 2xr. The second term there, which becomes x minus r times r square plus x square minus u over 2xr, and I have to divide everything by u to the power 3/2. Great. Now just like the previous time, we will simplify this. We'll get rid of the r and the r, and we will now rewrite this as gmm over 4xr times integral with the appropriate limits, and then everything inside the parentheses becomes 2x square minus r square minus x square plus u divided by u to the 3/2, and then there's also a 2 times x term that comes out, and all this will be multiplied by du. This ends up becoming gmm over 8 x square r times the integral of r minus x square and the limits. Now inside the parentheses all you have left is x square minus r square, and that I'm going to multiply by u to the minus 3/2 plus the u divided by u to the 3/2 gives you a u to the minus half with respect to u. Okay, we can carry out the integral now, so we get gmm over 8 x square r, okay, and we have x square minus r square inside. The u to the minus 3/2 will give me u to the minus half divided by minus half, and then the u to the minus half gives me u to the half over half. Awesome. Now we can further rewrite this as gmm over 8 x square r, and what I have left inside here are going to be, okay, so let's put in the limits, x square minus r square with a minus 2, and then what I have is 1 over a r plus x minus 1 over r minus x plus 2 times 1 over not 1 over, so the numerator here is simply r plus x minus r plus x. Let me close the brackets. We end up getting is all this gmm over 8 x square r is a minus 2 x square minus r square. Now this will simplify to negative 2x over r square minus x square plus 2 times 2x. Oops, there's no parentheses here. Okay, great. Very close to the answer. gmm over 8x square times r. Okay, now if you look at this, the negative 2x times 2, negative 2 gives us 4x. Okay, but we have an x square minus r square here and r square minus x square. So this gives us a minus 1. Okay, plus 4x, which ends up giving us 0. So what this result tells us that if you have a shell, if you have a mass inside the shell, this mass experiences 0 force due to the shell. So a shell does not do anything to any mass that is inside of the shell. So the only thing that the mass is affected by, or rather the shell will affect, is anything that is outside of the shell. Now we can also look at this qualitatively and realize that if we were to break the shell into lots of rings, okay, symmetrical about this object, all the rings to the left of this line, okay, will pull the mass to the left, and all the rings to the right will pull it to the right. Now even though we have more mass to the left, okay, compared with to the right, we realize that all these particles on the right hand side are farther away from this mass M. These guys to the right are closer to it, and that is why the net force ends up being equal to 0. Okay, so we have two important results here. One is that if I have a shell, okay, then the shell, essentially for all masses, all particles that are outside of the shell itself acts like a particle, and so the force that the shell exerts is simply gmm over x square, where x is the separation, the distance from the center of the shell to the mass. And on the other hand, if the particle is inside, if x is less than r, then the shell exerts no force on this object. Okay, so we will use this to figure out the force that a mass experiences once it tunnels into a solid sphere. Okay, because we'll break it up into a shell and a solid part, and we'll figure out everything else. Okay, so very important result. Let's make sure that we understand this.